So what I want to do in this video is just to talk about a few examples of power series. So nothing really new in this video, but let's talk about something like sine of z cubed. So this is going to be, and this is something that you could, just do directly. But let's just look at, this is the series from 0 to infinity, -1 to the k of z cubed to the 2k plus 1 over 2k plus 1 factorial. And let's say I just want to find the first few terms of the series. So this is going to be, let's see, if k is 0, we're going to get z cubed. And then minus, when k is 1, we're going to get, let's see, z to the 9th over 3 factorial, and then plus z to the, so we're going to get z to the 5th, so that's z to the 15th of, so that's z cubed to the 5th, so z to the 15th over 5 factorial, and so on. And in fact, what we could do is we could factor out, if you'd like, a z cubed from everything. And so this is going to be something that we'll look at going forward. Okay, we're going to be looking at zeros here. But here, this means that sine of z cubed is z cubed times some polynomial, g, and therefore sine of z cubed has a 0 of order 3. So we'll talk about what that means in a future video here, but that's sine of z cubed, so nothing terribly groundbreaking there. Let's look at a little bit more interesting. Let's look at, say, sine of z times e to the z. Okay, so sine of z times e to the z. And this is going to be two power series. Now, there is a formula for a product of power series, and maybe you've seen this formula. I don't care that much about the formula, but let me just mention it just in case. So if you have two power series, and I'm just going to look at power series centered at 0, you can adjust this for power series centered at whatever else you want. But let's look at the sum a sub n, z to the n, and I don't know why I'm using different letters here, it doesn't really matter. Okay, but b sub n, z to the n. It turns out that if you multiply two power series inside both of the radii convergence, then your product will also be a power series, and that'll be c sub n z to the n as n goes from 0 to infinity, where c sub n is going to be the sum as k goes from 0 to n of a sub k b to the n minus k. So there's a nice formula here, but don't memorize it. We don't have to think too much about this going forward. If we need to refer back to this, we can, but for now, let's just think about what's sine of z, what's e to the z, and then we'll multiply as if we're expanding out a product of polynomials. Sine of z, okay, we know is 1 minus z cubed over 3 factorial plus z to the 5th over 5 factorial, and so on. So minus z to the 7th over 7 factorial. And e to the z we know is 1 plus, so the Taylor series for e to the z is that we get z to the k over k factorial. So this is z to the 1st over 1 factorial plus z squared over 2 factorial, z cubed over 3 factorial, z to the 4th over 4 factorial, z to the 5th over 5 factorial, and so on. And then if we wanted to expand these, if we wanted to simplify this, what we can do is just straightforwardly multiply. And so we're going to get 1 times 1 is 1, and that's going to be the only constant term. And then if we want a linear term, what's going to happen is we're going to have the 1 from over here and the z from here. That's the only way we'll get a linear term. I have a mistake here, sorry. There are no linear terms here because this should be a z. I don't know what I was doing there. Sorry about that. That should be z minus z cubed over 3 factorial and so on. So when we multiply out, there are no linear terms. So the smallest we're going to get is z. I'm glad I caught that now. And then let's see, the next smallest term that we can get is plus z squared. So that's looking at the z and the z here. And then there's two ways that we can get a z cubed term. We can get z cubed here times 1, or we can get z squared times z. So we're going to get a minus z cubed over 6. So minus z cubed over 6 plus z cubed over 2. And then let's see, 1/2 minus 1/6 is 3/6 minus 1/6. That's 2/6. So that's 1/3. So that's z plus z squared plus 1/3 z cubed. And then let's see, can we get any fourth power terms? Sure. So we can get, it looks like the only way to do that is to get, there's two ways to do that. You can get z cubed here times z and z cubed over 6 times z. Okay, so let's see, we're going to get plus z to the 4th over 24 minus z to the 4th over 6. And so we're going to end up with z to the 4th over 24 minus z to the 4th over 6, and that's going to be z to the 4th divided by, so that's going to be z to the 4th. So what's 1/24 minus a 6th? That's negative 1/8. Assuming I did the algebra correctly, and that is an assumption. So it's negative 1/8 z to the 4th. And then you can do this until you're blue in the face here. Okay, but you can just do this as much as you like. But here now is our power series, okay, for sine of z e to the z. And again, if you want to memorize this formula and use it, fine, go ahead. I don't like memorizing things. I'd rather just sit there and figure it out, but that's how that works. So that's how you take the power, the product of two power series. Okay. I think the only other thing that remains is for me to talk about a few other examples of power series. And so a few other examples of power series would include things like you can talk about the natural log of 1 plus z. So if you were to talk about the natural log of 1 plus z, this is going to be the same integral that you would get for a real series. And so the way that this will work is that you're going to get, this is going to be the sum. I have to figure it out. Trying to find, we have a formula here. So this is, I can't find the formula, it doesn't matter. So this is going to be, we have to use the principal branch here. And so this will be the principal logarithm. And this is the integral, the antiderivative of the derivative. And 1 over 1 plus z is a geometric series. So you have negative z to the n as n goes from 0 to infinity, dz. And then we can integrate each side. So this will be the sum from negative 1 to the n, z to the n plus 1 over n plus 1, starting at 0, plus possibly a constant. And you can determine the constant by plugging in a value, say z equals 0. And it turns out that the c will be 0. So this is going to be from 0 to infinity, negative 1 to the n, z to the n plus 1 over n plus 1. And there's other versions of it. I think the way that the book did it, it might start at 1 instead of 0, but it's the same series. Okay, so this is the idea, and this is only valid if the modulus of z is less than 1. So the modulus of z being less than 1 was used exactly on this step because we applied the geometric series to 1 over 1 plus z. Okay, and so we can get power series there. You can get power series for arctangent the same way. It's the integral of the derivative. So I think that's really everything I wanted to say about all the examples of Taylor series and power series.